Hello, my name is Peter Zsivas. Welcome to the Computer Forensics course. In this course we will dive into the following topics: recovering files on NTFS file system and look for evidences, recovering files on FAT file systems, acquiring safe passwords from browsers and password managers, investigating users' internet activity by the help of browsers, history, cookie, cache files, getting the content of encrypted PST files, recovering some file types like Exchange MDB, NTDS.DIT, zip, and finally some introduction to memory forensics by the help of Volatility. In this video you will learn the working of the NTFS file system. We will examine how does the NTFS stores resident and non-resident files. Now we will examine the NTFS file system. First of all, you will need any Linux machine. I will use a Ubuntu 12.0 for long-time support version, but you can use any version where you are able to install a hex editor. So first of all, I log in with the password, with capital P password 1, and here is my computer, and I open a terminal. I already attached a second disk which contains an NTFS partition, and first of all I show you it. We change to root by the help of sudo -s command. It will ask for the password. It's again password with capital P and 1 at the end. So it was the password. And now let's list the disks. You can choose from many commands. One of them is the ls-brk, does the list block devices, and you can see we have here the SDA, this is the Linux machine, and the SDB, it will be our NTFS disk. Or if you don't like this command, then you can use the simple fdisk -l command. It's also list you all the disk. For example, here is the SDA, this is the Linux, and here is the SDB. This is our nice NTFS disk. There is only one partition, the SDB one. When we examine something, most of the time we want to examine the whole content of the disks. So almost every time we use the dev SDB as a driver, and not only the partition, the dev SDB one. So I will use this one. I enlarge a bit the screen to the size 83 times 33, because it will be the best when I use my hex editor. And then I'm going to install the hex edit. This is my hex editor. It can be done with the apt-get install hex edit. Okay, it's already installed. And then we can use it to examine our disk, the dev/dev/sdb. And here is our disk. When you open the disk, the first thing what you find is the master boot record, the MBR. It's here. And this is why I changed the resolution of the terminal, because now I can see exactly one block. The block is the basic size in case of the disk. Practically every time it is 512 bytes in decimal or 200 in hexadecimal. It's just depending which one you prefer. And now I just watch exactly one block with a screen. The master boot record can be easily recognized by its magic value at the end, this 55EA here. And we need some information from the master boot record, especially where does the partition starting. Oh yes, now during the first time I am talking about the master boot record, the MBR style disks, so not the GUID partition table. That will be some later stuff. Okay, as you know, in case of a master boot record style formatting, you can create 4 primary partitions. you are able to create only 4 because there are place for 4 partitions. You just have to find the last byte before this magic value, and this is the last entry, the first entry, this is the third entry, this is the second entry, and this is the first end partition entry. As you can see, the first one is 0, so practically there is no fourth partition. The third one is also 0 every byte, so there is no third partition. The second one also 0, so there is no second partition. We have only one partition, it's here. We have some important numbers here. The most important ones are the following. This first byte shows us if the partition is bootable or not, or if it is active or not. If it is 80, it means it is active or bootable. If it is 0, it means it is not bootable. The next important number here is the 07. It tells you the type of the partition. The 07 means the NTFS. Before the 07 and after that 0, there is the 02, 03, 00. This is the beginning of the partition in the old CHS notation. That's the cluster header sector notation. Practically today it is never used, so you don't have to take care of it. And this is the length of the partition in the old CHS notation, practically not used again. What we will need, those 4 numbers here, and this is the beginning of the partition in the linear block addressing notation, which works on the following way. You have to take this number as a little endian number, so 00, 00, 00, 80. So altogether it's 80. I open a notepad to write it down. So here, what I already know, the partition beginning at 0x80. So 0, 0, 0, 0, 0, 0, 80. It is measured in blocks. And as you know, the block size practically always 512 byte or 0x200 in hexadecimal form. Bytes. Okay. So we can calculate the beginning of the partition by multiplying these 2 values. It will be the offset. So the partition begins at the 80 sector or block, sorry, which is equal 0x200 times 0x80 equal 10,000. I will use a calculator to show you. I change it to programming form, change it to hexadecimal, and 80 times 200. It's really 10,000. So now we found where is the beginning of the partition, of our partition. So let's go there. We use the Ctrl-G command in this hex editor and go to the position 10,000. Sorry, my numlock was not turned on. 10,000. And as you can see here, really, the magic value of the NTFS partition. The magic value of it starts with the EB, that's the short jump, and it now jumps 52 bytes. This number can be varying, and here is an OP instruction. So practically just jump through the header, and the header now is hexadecimal 52 bytes, so 10, 12, 20, 30, 40, 52. So here continues the code, and this is the header itself. And here we can read some useful information. First of all, we need this 08. So this byte here, it's a 1 byte value, and this byte tells you how big is one cluster, because the NTFS organizes the data into clusters, not into blocks. So now it tells you one cluster built from 8 blocks. So I come here to my notepad and I write down the cluster size, which is 0x08 or 8 blocks. From this we can calculate that the cluster size is 0x08 times 0x200 equals 1000, but I show you 8 times 200, it's 1000 in hexadecimal, or if you want to watch it in decimal, then it's 4096 bytes. So this is the cluster size. Here you can read one more information. Just before this 08, there is this 200, it's 2 bytes value. 0, it's again in little endian, so 0200. It means one block is hexadecimal 200 bytes long. We already knew that because practically every case the disk block size is hexadecimal 200 bytes. There are some very few disks where it is different. So we know the cluster size, and the next information we need from here is the beginning of the master file table, the $MFT. It can be read here. So the start of the master file table, this is the $MFT, is at the position, again it is a little endian number, so 000000000001 54 55 position. So I write here 0x01 54 55. This is the starting cluster of the master file table, because in case of a file system everything is measured in clusters. So practically it tells you the master file table starts at this cluster. But because I'm using a hex editor, I have to calculate the byte offset on this disk. How can I calculate it? This is the cluster, so I have to multiply it with the cluster size. The cluster size is 1000, so I multiply it with the cluster size, and then I will get 01, 54, 55, and 1, 2, 3 zeros after it. It's easy multiplication. And of course it's a hexadecimal number again. But the file system measures this value from the beginning of the partition, of course, so not from the beginning of the disk. It's quite obvious because the file system knows only from itself, it doesn't know anything about the whole disk, and because otherwise why do we need any partitioning? So it measured from this position, so we have to add to this value this 10,000. So I add here plus 0x10,000, and if I up to it 10,000, it will be 1, 10, 100, and I have to change it by this one. So I added the 10,000, and now if I jump to this position, I should see the beginning of the master file table. So Ctrl G, sorry, 01 54 65, 01 54 65, and after that 3 zeros. And if I arrive here I will see something starts with file 0 entry, and it is a very good sign, because in case of the master file table, every entry starts with this magic value, this file 0 value. Now let's examine how does the master file table looks like. I will use the paint to draw you the basics of it. First of all, let's see, here is the master file table. This is the $MFT. Master file table. And the master file table builds up from blocks, and one block is always 1024 bytes long. So 1024 bytes, or in hexadecimal form it is 400. After it comes the next block, again with the same size. So it's again 1024, or in hexadecimal it's 0x400 bytes long. Okay, so this is the block, and it always starts with the magic value, what I mentioned, the file 0, and here also with the file 0. Every block contains one file entry, practically. So this is an entry, file entry, and those blocks can be divided into sub-blocks. We will have here, within those blocks, at least 3 different blocks. It will contain the metadata of the file. There must be always the so-called standard information block. It starts with the magic value 0x10. This is the number of it. There must be some file name block. It starts with the magic value 0x30, and we need some data block. It will start with the magic value 80, so this is the number of it. So we will have those kind of blocks. And there is one more important thing about the master file table. The first 35 entries are for system, first it starts to count from 0. This is what I want to say. So the first 35 entry belongs to the system, and it's count from 0, so practically the 35th one is your first entry. So we have to jump to our first entry, because the first entry is some system thing, it is the master file table itself. If I scroll down until the next one, this is the next entry. As you can see, it starts really at the position 400, so our entry is really 1024 bytes long, and this is the MFT mirror, and so on. There are some other system files required. And if I go to the first user file, it can be found at the position user file entry in master file table MFT. It will be the 35th entry, or in hexadecimal it is 0x23 times one entry is hexadecimal 400 bytes long, plus I have to add to it the beginning of the MFT, and it will give me the following value: hexadecimal 23, I'll show you it's really 35 in decimal form, multiplied with 400, plus the beginning of the MFT, that 1546 5000, almost 0. This is the 1546 DC00, so 0x 1546 DC 46 DC00. So this is the first user file entry. So let's go there. Ctrl G, 1546 DC00. Here, and here is my first file. Let's try to examine this file entry. As you can see, it starts with the magic value, and there is a header, and the size of the header can be read here. It's 0038, so altogether 38 bytes long, the header. So if I count here 10, 20, 38 bytes, then this is the header. And just immediately after the header starts the first block. As you can see, it is the 00000010. So this is a type 10. It means a standard information block. It's here. And the size of it will be 60. Here is the size of it, 00000060. So 60 bytes long, hexadecimal 60 bytes long. So this is 10, 20, 30, 40, 50, 60 bytes long. Just immediately after this block, there is the other block, and as you can see, the type of it is 30, so 00000030. It is a file name block, and it's 68 bytes long. 10, 20, 30, 40, 50, 68. So until the end of the line, it's practically here. And as you can read, here is really the file name, this a.txt. Immediately after this block, there is the next block. It starts with 80, so it means it is a data block, and the length of it will be 30, hexadecimal 30. So 10, 20, 30. So this is the data block. And here is one more important thing. This byte here, just after the size of the block, shows you if the file is resident or non-resident. The resident means if the file is short enough, then you have here quite plenty of place. So after the standard information block, file name block, data block, there is some space remaining. And if the content of the file fit there, then there will be the content. This is the so-called resident file. If the file is too long, then it is not able to fit here. Then the data block will contain the cluster chain which builds up the file. Now, as you can see, it is 0, so it means it is a resident block. If it is a resident block, then you have to check the following values. Here is this 18. Here, these 4 bytes. Again, it is little endian, so 00000018. It means from the beginning of the block, you count 10 and 18 bytes, and at this offset, we'll start the content of the file. So here we'll start the content of the file. Somewhere it will be the content. And just before this value, there is the length of the data. Now it is 16. Again, it is little endian, so 00000016. So hexadecimal 16 bytes. So 10, 11, 12, 13, 14, 15, 16. So this is my file. As you can see, it contains a lot of letter A. There is some enter somewhere in the middle. So we were able to find the file, and we were able to read the content of it. And now let's examine a bit more difficult one, non-resident file, and how it is built up in case of NTFS. To examine non-resident file, first of all, I press the Ctrl+C to exit from the hexedit, and then power off the virtual machine to attach a new disk. Settings, storage, I remove the resident disk. It was containing only this resident file, and I add the new one, and it is called as evidence NTFS non-resident VHD. I open it, okay, and start it. I log in with the password with capital P and 1 at the end. I open again a terminal, change the size of it to 83 times 33, because that's what I like. And then I change to root, so sudo -s, and give the password again, password1 with capital P. And again I list ls-brk, the block devices, or if you don't like this command, the fdisk -l, -l. This is the devices. As you can see again, the SDB is our disk. So let's take a look at it. I use the hexedit command /dev/sdb. Again, I examine the whole disk. Again, it contains a master boot record. So here at the end of it, this is the first entry, nothing, third entry, nothing, second entry, nothing. Here is only one entry, this one. And then so you can see, again, here is the start of the partition, those 4 bytes. So again, I can do the same calculation like before. Beginning of the partition, (0x80), and it is measured in blocks, and the block size, as usually, it's hexadecimal 200 or decimal 512 bytes. So it's 80 times 200, 0x200. It's altogether 10,000. So if I go to the offset 10,000, that should start the NTFS partition. So I press the Ctrl G to go to, and to the position 10,000. And here really the NTFS magic. And as you remember, from here we need this byte. It tells you the cluster size. So now the cluster size 0x8 blocks. It means 0x8 times 0x200, what is nothing else but 0x1000, which is decimal 4096 bytes. I take again the calculator, 8 times 200, it's really 1000, in decimal it's really 4096. So this is the cluster size, and the next information what I need is the beginning of the master file table. It can be read from here. It's always at the same offset. It's again 01, 54, 55. So the MFT, start of MFT, will be at the 0x, 01, 54, 55 cluster. So because it is measured in clusters, I have to multiply it with 0x1000, because this is the cluster size, and it is measured always from the beginning of the partition, because every partition has different clusters, of course they are not mixed. So plus 0x10,000. So altogether I have to calculate it again, hexadecimal 15455 multiplied with 1000 plus 10,000 with 1546,500. So 0x15465000. So this is the beginning of the master file table. As you remember, well, we can jump there, but we don't need really the beginning, because there will be only some system files. 15465000. Starts really here, there is the file 0, the magic value. But what I actually need is the user files. So start of user files, and it will be, you have to add to this value, so to the start of the MFT, plus there is altogether decimal 35 or hexadecimal 0x23 entry, which is only for the system. So the 23rd will be the first user file, because it is counted from 0. So I multiply it with 400, because one entry, as you remember, is 400 bytes long, or hexadecimal 400 bytes long. So 400 times 23 equals 8C, plus the start of the MFT, that's 15465000. It's 1546DC00. 1546DC00. So this is the position where the first user file entry starts. So let's go there. Ctrl G, 1546DC00. And here is my entry. This is the first user file entry. As you can see, it starts with the magic value. And let's examine this NTFS entry. First of all, we will need this value here. As you can see, it's 38. So the size of the header is 38 bytes long, hexadecimal 38 bytes long. So 10, 20, 38. So until here. Here starts immediately the first block, and it is a 10, so a standard information block. The size of it is 60, and as you can see, it is a resident block. The standard information block always resident, so it is not a surprise for us. So it's hexa 20 bytes long, so 10, 20, 30, 40, 50, 60. This is the standard information block. Here you can read information, for example. So you can read here data, for example, the creation time, the last modification time, the last modification time of the file record. This is the entry, so-called entry, and this is the last access time. So those are all together the so-called maze entries. The modify, create, access create and entry times. The order of them is the C, M, entry and access. Just it's a bit more difficult to pronounce on that way. So we have here those data, and here starts the next block. It will be a file name block, and it's altogether 68 bytes long, hexadecimal 68 bytes long, 10, 20, 30, 40, 50, 68. So until here, again the file is called as a.txt, and here starts the next block. So we can see it is an AT, so it is a data block with the length 48 bytes, hexadecimal 48 bytes, so 10, 20, 30, 48. So altogether until now, into this position. As you can see, it's a data block, 80, the length of it, and it's 01, so it means it is a non-resident block. So now the content of the file was not fit here. In this case, how to interpret the block? In this case, you have to take a look at this value here. And now it is 40. It means from the beginning of the block you have to count 10, 20, 30, 40 bytes. And here starts the cluster chain description. How you have to interpret this value? You have to take here the first byte, it's 31. So cluster chain. The first byte is 31. You have to interpret it as 3 and 1. The 1 means the number of continuous clusters are 8. So there will be 8 continuous clusters. And the 3 means the first cluster is described on 3 bytes. So 1 means we need 1 byte. This is the 08, and it will be the continuous clusters after each other which built up the file. And now it is 0x08. And the next one, the first cluster is described on 3 bytes. So let's take the next 3 bytes. 1, 2, 3. Again, it is in little endian, so 01 FE80. 01 FE80. So it is the first cluster of the file. So practically from this cluster, 8 clusters. Read 8 clusters. And after that I will find that 00. It means there is no more element in the cluster chain, so practically this file is not fragmented now. Okay, let's try to calculate this position and get the content of the file. Before we get the content, we need the size of the file. It can be read here. So from the beginning of the block at the position 20, that is where does the cluster chain starts, and at the position 30, here starts the length of the file. This is the real size of the file, and there is another one. This is the compressed, the initial data size practically, because if it is compressed, then it is two can be different. So this is the initial size, and this is the real size. We need now this value because, as you can see, it is not compressed now, both of them is the same, so practically unimportant which one you read. We need this one. This is the real size on the disk, and as you can see now it is 7F80. So size of the file, F80. Okay, now we are able to calculate the beginning of the file and the end of the file. Beginning of the file, it will be at the cluster 0x01FE80. And it is measured in clusters, so I have to multiply it with the cluster size, which is 0x1000. But the clusters are counted not from the beginning of the disk, but from the beginning of the partition. So I have to add to it the beginning of the partition, which is 10,000. 10,000. And if I calculate this nice value, I will get 1 FE80 multiplied with 1000 plus 10,000, altogether 1FE9 and 4 zeros. So 1F, E9 and 4 zeros. So this is the beginning of the file, and let's calculate also the end. As we see, this file now not fragmented, so it means there are 8 continuous clusters builds up the whole file. So practically we just have to add to the beginning file and to the beginning position the size of the file, which is 0x7f80. So it will altogether give me 0x1fe9 7f80. So this is the end position. Let's check it. I go to the beginning position, the 1F, E9 and 4 zeros. Ctrl G, 1F, E9 and 4 zeros. And here starts some letter A. This is the content of my file. And if I go to the 7, I went a bit too much, 7F80, really, after that came only zeros, so most probably this is the end of my file. Of course it is really that, because we read it from the NTFS, from the MFT entry. So this is how you can find the content of the file. Of course, if you want, for example, you can use the DD to dump this file to your disk and examine it. You can do it on the following way. You have to use the DD and give it the IF, the input file, equals /device/sdb, and we give it some output file, OF, equals, for example, to the actual directory, I create an a.txt file, and the block size now 1, because this is the easiest to count with, and I keep the first hexadecimal 1F E90000 bytes. So I change it to decimal, this value. Okay, 53, 60. And 584. And count. I want to copy the size of the file, as you remember, is 7F80. In decimal, it is 32,640. So 32,640 bytes. Copied. If you use, for example, nano to open this a.txt, then really, here is the content of my file. This is the end of it. So this is how you can find the content of a non-resident file in case of NTFS. And let's try to examine some more things.